Hi, good morning or good afternoon. My name is Sofia Gomez, and today I'm going to be giving a talk that is on the strength of sintered alumina lattices and their effects of purity and density on their strength. So the agenda for this topic is as follows. I'll be introducing the materials and methods used for this work. Then I'll be giving a brief overview of the publication, which is on mechanical strength of 94% alumina octet lattice structures. Then I'll conclude with some key findings as well as make suggestions for future work. With that being said, I would like to introduce ceramics. So ceramics are materials that are non-metallic and are inorganic and are typically processed at high temperatures. We can actually classify ceramics by their function. Some ceramic types include silicates, which are porcelains, non-oxides, which are carbides and nitrides. Composites can refer to the mix of the two, such as non-oxides and oxides. And finally, oxides can be anything from magnesium, calcium, and aluminum oxide, which is a material of interest for this work. The material properties for alumina include electrical insulation, which is desirable for microelectronics. They are oxidation resistant, as are all oxides, which makes them suitable for nuclear reactors. They're also chemically inert, which is why they can be used for bone prosthetics, and they have a high melting point, high stiffness, and high strength, which makes it suitable for aerospace applications. So vat photopolymerization is the 3D printing technique that I use for this work. VPP for short is an additive manufacturing method that requires a photosensitive slurry to be used so that a light source can cure the slurry layer by layer within the vat. And there's multiple subsets of this technology, but we decided to use LCM, which is lithography-based ceramic manufacturing. It's a method that uses a ceramic slurry that is dispensed to a transparent vat. Then the movable build platform is dipped into the slurry before being exposed to a visible blue light. Each layered image is projected onto the slurry, and it's produced by a digital micromirror device in combination with a projector. This process repeats until the 3D printed part is completely built. So when choosing a lattice structure design, we should think about how it will impact the mechanical response. We can actually infer this behavior of lattices by understanding its unit cell and macro scale topology. There are many different types of lattice designs, however, we can use a few to describe their mechanisms. There are two different types of mechanisms, so there is a bending and stretching dominated mechanism. And we can classify these mechanisms of our lattice structures by using the Maxwell stability criterion, where S is the number of struts and N is the number of joints in the unit cell. If the number is below 0, that it means that it's a bending dominated structure because after load is applied, the struts bend because of lower nodal connectivity. When the number is equal to or higher than 0, then it means it's a stretch dominated structure. That means when load is applied, it actually produces tension between the middle of the nodes and compression from the outer nodes, causing this to be a stiffer type of lattice. We can actually predict the modulus and strength of lattice structures through the use of the Gibson-Ashby model, which is widely accepted and used amongst researchers for numerical modeling predictions of cellular solids. The Gibson-Ashby model relates the relative density of a cellular solid to its relative strength and relative modulus using this equation below. Previous work from Gibson and Ashby along with other researchers can actually be seen from this plot here to the right, where they used experimental data to fit their curve. And we can see that as relative density increases, the relative modulus increases as well. So now I'll be talking about my publication, which is on mechanical strength of 94% alumina octet lattice structures. As previously described in the introduction, the Gibson-Ashby model was created so that we could accurately predict properties of cellular solids based on their relative density. Now, the advantages of cellular materials are that we can use them to optimize stiffness and strength with a relatively low density. As for 3D printing lattices, we could leverage a shorter sintering time and mitigate warpage. However, the only shortcoming of the Gibson-Ashby model is that they validated it mostly with metal and polymer materials, which behave much differently mechanically. In addition, there are no standards written for testing ceramic lattice structures, so most researchers use the ISO standard for metal lattice structures, For this work, I used the octa-unit cell design seen here and translated it 5 times in the XYZ direction to form a lattice structure. I changed the strut diameters from 0.25 to 0.5 to 0.75 and 1 millimeter to change the lattice densities. I made the following design of experiments for this work. So the goal of this work was to correlate the mechanical strength of the lattices based on its strut diameter and alumina purity. So what we did is we 3D printed lattices using 2 different alumina purities, a 99% alumina and a 94% alumina. We also made 4 of each lattice type and varied the strut thickness. So there were a total of 16 lattice structures printed for each alumina and 32 lattices total overall. Every single lattice was put through the entire thermal post process, and all samples were characterized using density and dimensional analysis, compression testing with DIC, which is digital image correlation, SEM analysis, and the Gibson-Ashby model fitting. So we originally designed the lattices to be 20 by 20 by 20 millimeters. However, as seen in this photo, the struts were damaged when removed from the build platform. So then we decided to create the lattices with a top and bottom plate that was 1.5 millimeters thick. We made these open areas to help them with sintering, and then we set the layer thickness to 25 microns, which is the highest in the Z resolution. We made these sample holders to keep track of all of the lattice types. The ones in the red sample holder would be the 99% alumina, and the ones in the gray holder are 94% alumina. We also took images of all the lattices side by side, as seen here in the bottom. The lattices labeled HP refer to the 99 high purity alumina, and the 25, 50, 75, and 1 refer to the strut diameter. The lattices labeled P refer to the 94% alumina lattice structures. So we calculated the shrinkage of the lattices after sintering for all lattice types. I measured the green, X, Y, and Z lengths and tracked that same sample to measure the sintered lengths. So to calculate the shrinkage, I used the green length and subtracted the sintered length and divided it by the green length. For both alumina types, the Z shrinkage was found to be the largest from the XY dimensions, and when X and Y were analyzed, the 94% alumina had a higher shrinkage rate than the 99% alumina. This result was also seen in these plots here, where we correlated the Z and Y shrinkage to the design strut diameter. There was no correlation seen as a function of strut diameter. However, the shrinkage was larger for 94% alumina by about 6%. The density measurements were calculated using a variety of methods. The bulk density of alumina was measured using the Archimedes principle, where we measured the mass of the sample out of water and then in water. Since there's porosity, the bulk density differed slightly. The reported theoretical density was found in literature, and the lattice density was measured by taking the mass and dividing it by the measured volume. The relative density was then found by dividing the lattice density by the bulk density, and the porosity was measured by subtracting 1 from the relative density. The measured bulk density differed from the theoretical density because of the presence of voids within the sample that filled with water. The thicker the strut diameter, the closer to the bulk density was to the theoretical density. Overall, the 99% alumina had a higher density than that of the 94% alumina. So we did an X-ray fluorescence analysis of the sintered lattice structures to see if the silicon migration was apparent, as seen here in the bottom left-hand side. We found that in another publication after sintering that there was actually silicon migration. Both aluminum and silicon maps were produced for both alumina purities, and the results showed that the 94% alumina has a pretty even distribution of silicon with a few instances of agglomerates, and the 99% alumina had very minimal silicon presence. Digital image correlation, or DIC, was used to track the actual displacement of the crossheads during the compression test. We calibrated the system using the grid, and if you take a look at the grid here on the top right, we see that the grid has white dots, some with holes, and the dual camera system can detect these features, and it actually takes a picture when the feature is detected. So once a certain amount of images was taken, we received a score, and if it was less than 0.1, then it was sufficient. For the compression test, we set the crosshead speed to 0.1 millimeters per minute as specified for ISO standard. When the lattices failed, then the test was manually stopped. So these were the images that were taken during the compression test. We took one image every second, and the test lasted about 2 to 5 minutes. The beginning to the end of the test is seen from left to right, and the left images are of the 99% alumina lattice structures, and the ones to the right are the 94% alumina lattice structures. All the lattices fractured diagonally with the octet lattice design. This behavior has actually been seen previously by other researchers. And we also saw that the lattices that had larger strut diameters fractured more catastrophically and behaved more like bulk alumina. So the result of the compression test for HP alumina lattices are shown here in the stress strain curves to the right. A is from HP 25, B is from HP 50, C is from HP 75, and D is from HP 1. So from the stress strain curves, we see that all lattices showed elastic deformation in the beginning of the test. For HP 25, local cracks and fractures initiated at relatively small compressive loads, leading to stress fluctuations throughout the test. For HP 50, there were still some local cracks, but they recovered and were less fluctuations. For HP 75 and HP 1, we saw that they had smooth stress strain curves that failed abruptly like bulk alumina. And we see that as relative density increased, so did the modulus and strength. So these are the results shown in the stress strain curves to the right for the P alumina lattice structures. From the stress strain curves, we see that all lattices showed elastic deformation in the beginning for the 94% alumina as well. For P25, the local cracks and fractures initiated at a relatively small compressive loads, leading to stress fluctuations throughout the test. At P50 and P75, there were actually less fluctuations in stress that there were result of struts being fractured locally layer by layer. The fluctuation in stress may also be a result from silicon conglomerates as seen in the XRF analysis that were caused by premature failure due to poor interlayer adhesion. P1 shows a more distinct stress strain curve with a linear region and a sudden stress drop. So once we calculated the lattice modulus, we were able to start fitting our experimental data to the model. We plotted the relative modulus as a function of relative density on a log scale plot, then found the equations to the curves for 94% alumina, which would be the top curve, and 99% alumina, which would be the bottom curve. We found that the constant was a value before x, and the exponent was the exponent following x. When I did the calculations for predicting the modulus, we got a relatively low percent error for 94% alumina when compared to 99% alumina. So then we followed the same procedure for fitting the compressive stress data. However, we found a significantly large error for 94% alumina and a large error for 99% alumina when compared to the predicted modulus results. The exponent of 2 suggested that the lattice being compressed formed in the bending dominated way, which was incorrect. It is possible that the fitting of the strength had a higher percentage error because of the different fracture behavior exhibited by ceramic lattice structures when compared to metallic and polymer materials. Ceramic materials do not yield, they just reach a maximum strength. So SEM was used to look at the fractured surfaces of the 0.25 millimeter strut lattices. A through D images were taken of the HP lattices, and E through H were taken of the P lattices. In A and E, we see a close-up of a fractured strut somewhat far from the node. We also see that the surface finish of HP is a lot smoother than that of the P lattice structure. When we compare B and F, we're looking at a close-up of a bottom plate. Again, the fractured surface and normal surface for P look almost identical. In images C and G, we can observe the way that the parts were printed by looking at the layer-by-layer design. In G, the layers are very distinct, possibly from poor interlayer adhesion and P alumina. When we look at the broken strut closer to the node, we see that there's a high surface roughness in both D and E and H images for both alumina purities. So again, we used SEM to look at the fractured surfaces of 1 millimeter struts as well. Images A through C were taken of HP 1, and images D through F were taken of P1. When we look at B and E, we can see that the fracture took place in a specific spot in the middle of the node. And A and D are close-up images of the broken node. It appears that P particles in D are very angular, longer, and larger than the particles in HP1 alumina. When we did a close-up of the unfractured strut in C and F, we see that the particles in C are more closely packed together than the P particles in image F. As shown before, we know that there was a liquid phase sintering that was induced by magnesium, calcium, and silicon at high temperatures. Since there was a rearrangement of like particles, it may have been a result of small pores seen in F, and therefore leading to pore packing and ultimately lower strength and modulus. So in conclusion for the publication, we saw that as far as dimensional analysis, that the shrinkage rate for 94% alumina was higher than the 99% alumina due to it being less pure. Since it was less pure and it had elements such as magnesium, calcium, and silicon, it induced liquid phase sintering in certain regions. When we looked at the XRF results, we saw that the intensity maps revealed silicon content was dispersed throughout the lattice after sintering, although we did see some instances of silicon agglomerates. Using the DIC analysis, we saw that the octet lattice structures failed in a diagonal orientation, and when we used a higher strut diameter, essentially they exploded from uniaxial compression. From the compression test results, we saw that the high purity alumina had a higher modulus and compressive strength by an average of 63% and 144% respectively. When we used the Gibson-Ashby model, we saw that the P alumina lattices had a lower percent error after fitting the equation to the experimental data. When we looked at the images using SEM analysis, it revealed that the HP alumina had a better surface finish over P alumina after sintering. And we also saw that larger strut diameter fracture behavior changed drastically from thinner struts. In the future, for this work, I would suggest to test different loading rates for compressions of alumina lattice structures, since the standards that we used were based on metallic lattice structures. I would also suggest to use EDS analysis on broken nodes and edges after compression to see what sorts of elements are on the broken surfaces. And I also suggest to analyze the effects of different percentages of silicon content into alumina powder and see how that affects shrinkage, mechanical, and physical properties. And well, that's the end of my presentation. If anyone has any questions, please feel free to reach me at this email. Thank you.